Welcome back to Probability, Logic, and Beyond. In previous videos, we looked at various discrete random variables in which the probability of the random variable was constant over time. In many cases though, the probability of events occurring changes with time and can depend on a variety of factors. Suppose we're trying to predict the weather. If we know today's weather, we could use that information to better estimate what tomorrow's weather will look like. If today is sunny, for example, it might be very likely that tomorrow will be sunny or cloudy, and unlikely that tomorrow will be snowy. If today is rainy, on the other hand, it might be more likely that the next day will be rainy, cloudy, or snowy. Each state will have a probability distribution describing the likelihood of arriving in all the other states in the system. This kind of model, in which the probability of the next event depends only on the previous event, is called a Markov chain. This is the key simplifying assumption that separates Markov chains from other dynamic state models. We can express this assumption mathematically like so. This definition is quite intuitive, and it just means that the probability distribution of future t+1 states depends only on the most recent state at time t. To visualize the probability distribution of going from state to state, we typically arrange states in a graph-like structure. Then, we use arrows to represent the probability of transitioning from state to state. Let's assume that today is a sunny day. Given this information, we know that the probability that tomorrow is sunny is 60%, the probability that tomorrow is rainy is 10%, the probability of a cloudy day is 25%, and the probability of a snowy day is 5%. To traverse the Markov chain, we can sample this random probability distribution to get the next state. Suppose tomorrow ended up being cloudy. Then we move to the next state in the Markov chain. Now, the probabilities change. The day after tomorrow has a 20% chance of being sunny, a 20% chance of being rainy, a 45% chance of being cloudy again, and a 15% chance of being snowy. We can continue to move along this chain at each time step by simply sampling from the probability distribution described by each state. In many problems, we're given the entire chain at once in a graph-like structure like this one. It's quite intuitive to move from node to node in the graph. However, we don't need an image to describe the behavior of the system. Instead, we can define what's called a transition matrix, P. The transition matrix defines the probabilities of changing from state to state. Each row in the transition matrix represents the probability of moving from the state defined by the row index R to the state at column C. All of the information present in the graph visualization is elegantly contained in the transition matrix. There are two important things to note about the transition matrix. First, each row in the transition matrix sums to 1. This is because otherwise the sum of transition probabilities would exceed 100%, making it an invalid probability distribution. Secondly, every element in the transition matrix is non-negative. In many questions, we might be interested in the probability distribution of the states at some point in the future. For example, what if we're asked something like, given that today is snowy, what's the probability that it rains in 2 days? To tackle this problem, we need to understand two more key concepts. Firstly, the state vector, P, is the probability of being in state I at time t. Because today is snowy, the state vector at time t equals 0 is 0, 0, 0, 1, as the snowy state is the state at index 3, and we are there initially with 100% certainty. The second concept we need to understand is how to update the state vector over time. To do this, we just multiply the state vector by the transition matrix. To get the probability distribution n days into the future, we multiply the state vector by the transition matrix n times. Thus, to solve this question, we just need to multiply the current state 0, 0, 0, 1 by the transition matrix twice, which gives a probability distribution of 0.165, 0.23, 0.235, 0.37. Because all of the rows of the transition matrix sum to 1, and there are no negative values, the state vector will always remain a valid probability distribution. We're interested in the probability of it being rainy in 2 days, which is the value at index 1, so there's a 23% chance of rain in 2 days. The transition matrix helps us move from state to state. It also helps us determine the probability distribution of the states at some point in the future. The transition matrix also gives us some information about the state, even if we don't know anything about the starting state. For example, what if we're asked to determine the probability of it raining with no information about the start state? This is called the stationary or steady state distribution. The stationary state is a state that is unchanged by the transition matrix P and is not affected by time. There are 2 conditions for the existence of a stationary state. First is the transition matrix cannot have any cycles, and the second is the transition matrix cannot have any absorbing or transient states. There are many ways to determine the stationary state of a Markov chain, but we're going to focus on 2. The first method is a sort of brute force method, and it's called the power method. In this method, we continuously apply the transition matrix to some initial state until we converge to a stationary state. The second method is setting up a linear system of equations which we can solve manually or with a solver. We can see from this snippet that if we move pi to the left side, factor it out, and then take the transpose, we have a pretty elegant solvable system in the form of ax equals b. We can choose to solve the system ourselves by hand, or we can just simply plug it into a solver in Python. Now that we've learned about stationary states, let's summarize our learnings. We started off by learning about the key assumption underpinning Markov chains. That assumption is that the current probability distribution depends only on the distribution of the most recent state. This is also called the Markov property. Next, we learned about the transition matrix and how we can use this matrix to compute the probability of future states. Third, we learned that stationary states are states that are unchanged by the transition matrix P. Finally, we learned about 2 ways to determine the stationary state in the power and linear system methods. In future videos, we'll use what we learned in this video to conduct simulations of various systems that depend on Markov chains. Thank you for watching, and please subscribe to the channel for more content on probability, logic, and beyond.